Okay. Okay, thank you for the invitation and the introduction. Today I'm going to talk about a proposal for non-abelian mirror symmetry. And so it's based on four papers. So this is archive number. So this topic is concerned with non-abelian mirrors. So for abelian mirrors, so abelian theories, many things are well known. So for example, abelian GLSMs are well understood. In math, there exists battery Orbifold construction of mirrors to complete intersection in projective space. Also, in physics, we have Hori and Vafa mirror constructions. For non-abelian theories, there still remain a lot of work should be done. So non-abelian still active research, and no non-abelian mirror construction in physics until 2018. I apologize that I will not talk about the difference between physics and math construction. I know in some math community there's some construction about non-abelian mirror, but I will not talk about that in today's talk. So in the main content in this talk is I will first quick.
You will tell us if your mirrors agree with what Reich and others have done, right?
Sorry, say it again.
You will tell us if your proposals for mirrors agree with what Reich and others have done.
I will not talk about that in today's talk. But I will check because mirror, I will check the consistent with the A side, the gate zero side. Yes, I will quickly review what gate linear symbol is and what's the Hori-Vafa mirror construction for abelian gate linear symbol. And I will propose mirrors for non-abelian gate linear symbols. And then because the proposal, you will know why I say it's just proposal. So we have to check example to guarantee our proposal is right. Hori-Vafa itself is a physical derivation, so they claim it's a physical proof. We didn't claim that. So because we talk about mirror symmetry, and let me just briefly review what I mean by mirror symmetry in my context. I just
at the same time, I mean, Hori and Vafa was 20 years ago, right? And yes, since then, mathematicians have proofs of homological mirror symmetry based on Hori and Vafa, and it's been studied to death. So, I mean,
okay.
When you can't just say, well, it's okay.
Maybe I say something not precisely. Maybe we can talk about it later. Okay. I just focus on closed string, so I don't talk about brain in this talk. So usual mirror symmetry for if you have a Calabi or mirrors, so there's very elementary ingredient of mirror symmetry is that the cohomology class have such quality. For 3-4 Calabi, there's a long trivial phenomenon in math that the Euler characters for the Calabi or X will become is a minus sign or Euler or the mirror Calabi. In physics, we can use worldsheet to probe this Calabi, and for Calabi, targets the worldsheet will flow to a CFT, and the mirror symmetry is simply just a convention or left U1 asymmetry sign convention. For example, the HPQ become H minus PQ, and using homological form, we can map to HN minus P, comma Q. But today I will talk about the more general class, not just focus on Calabi. We can talk about funnel. So it's a massive theory. So we have to. So in my context, my mirror symmetry is exchanging a Kähler multiplier and a twisted Kähler multiplier. So in 3D community, they call it exchange the Coulomb branch and the Higgs branch. They all should be gate invariant. So because gate linear symbol contains both ingredient, twisted Kähler and the Kähler superfield. So I will quickly review what gate linear symbol is. So gate linear symbol have been studied extensively in the literature. So we define gate symbol by specifying the following data. So a compact Lie group G with associated Lie algebra small g. And then we also have Kähler metal field phi I. So it's a irreducible representation or the compact Lie group G. And this vector space denoted by Cn. So also it's a gate theory. So we have a John field V is a general rotating of G, and it has a field strength superfield. This sigma is a trace scalar superfield. And we also, if you consider GLSM symbol for hypersurface or complete section, we also need GLSM symbol have a superpotential at the UV. Yes, we also have a parameters called FR parameters, and also like 4-dimensional QCD, we can also turn on theta angle in 2 dimensions. And these 2 parameters can linear combination to define complexified parameter. We usually call it Kähler parameter. And we define Q to equals exponential minus T is C star variable to capture the instant correction. Because this 2,2 SUSI, we also have a asymmetry. We have a left and right and linear combination will give you 2 independent vector asymmetry and external asymmetry. And the superpotential should be have a asymmetry 2 under our convention. In math, they may give a convention 1. Okay. So if you give a Gaussian symbol, we usually find the ground state by get the classical potential energy, and using the potential we can find ground state. Then give you the field vacuum expression value. Then expand your field around this vector expected value. You can go to algebra flow. For example, if you consider CPN, then if you're solving mu equals 0 and we get geometry phase, the I is positive, then this one equals 0 will tell you that some phi I minus T equals 0. But this should be R, sorry. And because CPN, there's no hypersurface, there's no such term. And no such term doesn't require the sigma, because this means at least 1 phi non-zero. So it means that sigma must be 0. Then we expand the field around this vacuum expectation value and integrate out the modes, massive modes around this expansion. Then the theory will algebra to a non-linear symbol on CPN. And the Kähler parameter is normalized under this algebra flow. Then this the R by some such correction, the R by Bell value defined. We define the UV. If you copy out some QI equals 0, there's no correction. This is what is differential safety. Okay, for CPN, for CPN, in Wheaton's paper, there one key point that for CPN, we can also define the theory when the R is smaller than 0. However, in this situation, the mu here have low solution. So this means there's no classical vacuum configuration. Then what he proposed that we go to larger sigma, then integrate out the phi field. So go to the Coulomb branch. So today I mainly focus on final case to check the mirror proposal. So I also use a Coulomb branch later on for the study. So what's the Coulomb branch represent in 2-dimensional quantum field theory? So by Wheaton, we can know that the sigma can be treated as a generator, or for example, for CPN, the sigma is generator or H11 up to a mirror map. For this case, mirror map is trivial, so I can simply treat sigma as a generator or H11. Okay. Yes. Yeah. The twist effect superpotential. I mean, by integrating the matter field, we induce one-level correction. So this term is due to one-level correction. Then the vacuum, the quantum vacuum, it can be the partials to the partial sigma equals 0. Actually, the precise way is exponential. This one equal 1 could be more precise. A little bit imprecise here. And so this one will give the quantum cohomology ring for the final space if we have low non-trivial Landau Ginzburg at Landau Ginzburg at an LG point. Okay, I just review what the Gaussian symbol is, and I mainly focus on final space. Then I can use Coulomb branch to do the computation. Now I can review what I mean by abelian mirror. So for abelian mirrors, the mirror is Landau Ginzburg models with fields. So we have Yi neutral fields. So it's mirror to each matter fields in the Gaussian model. And it's a 2 pi I periodicity. So the right variable should exponential minus y. We also have a sigma A, which are optional fields. So it's a mirror to the gauge field strength or the original gauge, but we use the same notation. So it's a non-Ginzburg series, so we have a superpotential rather this way. So if we know the charge data or the gauge model, we can have a framework to write a mirror non-Ginzburg in terms of this way. Okay, so the non-Ginzburg series has a very good property. For example, the Kähler potential is irrelevant in 2D quantum field series. So I will not talk about them, but I will assume they're flat when I use them to do the computation. And also there's a non-renormalization theorem for the non-Ginzburg superpotential. So the vacuum can be computed straightforward, that just like we did for Jacobian ring, that partial W partial Y equals 0, define a quick rule psi, because the potential energy is this square. Of course, I have to give you Kähler potential to Kähler metric to define that, but I'll be stopping here. And from the non-Ginzburg, I start with I define for the mirror, so we can take a derivative for yi to get a map between the sigma A, the sigma A field and the exponent minus y with such equality. So this one I said this one is a trace Kähler field in the gauge series side. So this one is a Kähler field in the mirror. So the mirror, this will give you a map between the variable in the gauge series side and the variable in the mirror side. I will use this map to do the concrete computation. Maybe a quick example is CP4. And I use this is a pure massive theory. I can use the proof. So it's a U1 gauge series with 5 Kähler superfield. All have gauge charge 1. So in the A model, the twisted superpotential can be just plug in the data or the charge cube. You can this gives you a twisted effect superpotential. Then we can use this to get a ring twisted Kähler ring relation. Just partial W to the partial sigma equal 2 pi I, and then it will give you sigma to the power 5 equal Q. This one is polynomial. It's part of 5 polynomial, so it have 5 solutions. So it's a give a write a vacuum number. So because CP4 have all our characteristics is 5. Also, we can compute the correlation function. So the classical, like I said, the mirror map is trivial. So sigma can map a hyperplane class to the CP4. Then h to the power 4 equal 1. Then I insert the Kähler ring with some power, positive power insert this calculation. Then we'll get such correlation function. One can also get a similar result by studying instant modular space. So I will not talk about that. So the mirror model for CP4, because we know the Q, just plug in the framework, we can write the superpotential is this. Then we usually in mass. So this one is not going to define UV in mass because the mirror symmetry mirror is non-linear symbol to a no energy for the Ginzburg series. So we have to integrate some Roxton field. So integrate sigma will give a delta function or the some yi minus t. Then I integrate the last variable phi y5. We solve this delta function, then restrict your series to a low dimension. So right now it's 4 dimension. And we know CP4 is 4 dimension. Really, indeed it's 4 dimensional. And with such superpotential, must mention you write the x instead of exponential minus y. And then they also choosing q equal 1, but I don't know the reason. Anyway, I write it this way. So on the Ginzburg, we can compute a Jacobian ring, just partial w partial y equals 0. It will tell us that all the exponential minus y, all the exponential yi at the infrared, they are same equal x, and x to the power y equal q. So this, if you map a sigma to x, so indeed this gives the same Kähler ring in the gauge series side. Of course, yes, this correlation function B model can be computed by Hori and Vafa in 1919. So this one can be computed exactly. Of course, we can start a mirror for hypersurface in projective space as well. They will require some knowledge about the orbifold twist sector and C0 and A0 and some kind of safety technique. I will not talk about them today. Okay, let me pause here for questions. Okay, if no question, I'll continue. So in 2 years ago, we proposed that the mirror for non-abelian Gaussian so with collect gauge group G is defined by a Landau Ginzburg orbifold, which is a Y group or Yi and X nu and a sigma A field with a superpotential only field space. So this superpotential, can be if we know the weights or the matter rotation for the gauge theory side, we can know the data of rho AI. And if we give a group G, we can tell if it can tell the roots, so we can plug in the roots. Then we can write a mirror explicitly. Of course, you will see that this is a log X mu, so this is effective theory. So you cannot using UV perturbative theory to start it. It means that you cannot treat the sigma W as perturbative correction. You have to treat this as effective theory. So the sigma A is a mirror to each U1 gauge field strength multiplied in the Cardan torus or the latter non-abelian compact group G. A Yi mirror to the matter field, just like we did for abelian case. So we have actual ingredient is a mirror to a double boson. And this one is, I know it's confusing. I will give a comment about this later on. So it's a loose order the algebra. So the Weyl orbifold map is an orbifold theory to map Yi to Yj and a sigma A rho Ia map to in this formula. So one can check that the superpotential is gauge invariant. And this our theory is a well-defined gauge theory. So the idea of proposal. So for Gaussian model, for non-abelian model, the dynamics is very complicated. So we go to GLSM branch. So it's an effect theory. So the non-abelian theory becomes the abelian theory with double boson. So this double boson is the lowest component or the Kähler superfield with vector archive 2. You may be confused because double boson originates from vector multiply. But why we treat this as a Kähler multiply? The reason is that double boson is charged by the left maximal torus or the non-abelian group. And if you treat and we know if you want the SUSI, it should be if you still want the SUSI, only Kähler multiply can be charged by the gauge group. So this means that double boson after non-trivial arch flow become a Kähler superfield. But it's not just trivial, it's not a usual trivial Kähler superfield. It must have archive 2. The reason to argue archive 2, there's 2 reasons to argue archive 2. If you see for CFT at IR, the vector multiplier will contributing a negative sign in the negative sign in the safety central charge. We know that archive 2 also contribute a negative sign. So this is one evidence. Also, if you last decade, there are many exact results tell us that if you assign this as archive 2 will give the same, give the right exact result. So this is the reason we argue this archive 2. So this is effective theory. So our intuition that the non-abelian proposal is a result that apply abelian duality at such point. So to both the matter field as well as the double boson. So this is the reason why we will close to the abelian duality. So the logic is that we start from UV non-abelian, but we take duality or effect theory that looks pretty like an abelian theory. And the effect theory is conjectured to follow the same non-abelian model as the original non-abelian model is. But we don't know how this arch flow take going. So we don't know how the Kähler potential change from the non-abelian to this effective Gaussian model. So we didn't claim we have a proof, but we just give a proposal. And if we find a non-abelian T duality, it maybe have a chance that we give a mirror is UV fundamental theory. And this fundamental should be give the same low energy theory as our non-abelian mirror. And it will give a reason, it will tell the reason where the freedom degree is missing in our superpotential. There's a pole here. Maybe if you have non-abelian T duality, we can tell what's the freedom degree missing around that pole. Okay, maybe let me give you quicker data about associated Cardan because I didn't really T duality non-abelian theory. I T duality effect theory or latent non-abelian theory. So the latent effect theory is called associated Cardan. It started by Jeff Harrison and Morrison and I forgot the another order, sorry. And then the gauge group is a maximal torus or that non-abelian group G. So with the T is this maximal torus and with a Weyl group S. So this Weyl, yes. And the calorimetric field is charged by this.
Sorry. Can we slow down a little bit? So I might want to know something like a mirror of, say, of a Grassmannian, right?
Yes.
And a priori, if I tell you I want a mirror of a Grassmannian, I don't really care whether you describe it as a nonlinear sigma, like a gauge sigma model or not, right?
Right.
Right. And but okay. So your description here hinges on having a description as some quotient, right? By a non-abelian gauge group.
Yes. G quotient, V mod G. Yeah.
Right. And then, so in the linear sigma model case, right, what I recall is Witten argued that in his original, the argument was that there are no phase transitions in 2 dimensions, right? So you should be able to, so even if you're interested about a theory on the Higgs branch, Grassmannian, we should be able to go onto the Coulomb branch and learn something about it.
Yes, right? Yes.
And your hope is that this should hold also for these non-abelian theories as well.
Yes.
Which is a reasonable thing to hope, but one would. Good. Okay.
Yes, you're right. But for non-abelian, sorry that for the because we want to integrate the double boson, which is off diagonal turn, is a heavy matter field in the Coulomb branch. If you integrate out, that one will not tell you the data about the Coulomb branch. We're missing some data, but it will definitely tell you something. You're right, you're completely right. But yeah, I will go to that point.
Now, when Hori and Vafa wrote their paper, okay?
Yes.
Well, they followed physics arguments, which is great, but they also had a check. They had a check which was Giventhal's work, which they essentially generalized. The Giventhal's results for CPN had already been known. Right. Now,
I don't know.
Non-abelian theories like Grassmannians, or even cotangent bundles to Grassmannians, the analog of Giventhal's results are known, because mathematicians had many years to be able to calculate,
okay.
Or even on, T-star Grassmannian. It's not that hard, right?
Yeah,
so I wonder if you've compared your physics results to those, because the assumptions you're starting with are reasonable enough. Well, it would be nice to see some checks. Will you show them to us?
First, I enter this direction without have any mathematical training. So I just find it interesting. I want to solve that. So I don't know Giventhal's work before. And my proposal not just focus on Grassmannian. I can study.
Yeah. I mean, but you can't work in vacuum. You have to pay attention to the results that people have because they're a guide, right?
Yeah, you're right. But
okay.
in this talk, I just focus on to tell us
in fact, something. In the audience, we have here Ivan Danilenko. Okay, he basically provided analog of Giventhal's results for the spaces you're interested in.
Okay,
go ahead.
Okay, thank you. So
the question, so just to make sure I understand. So you have basically you're saying that you flow from UV to IR, right? And then you apply T-duality in the infrared when it's abelian, and then. But can you read off the dictionary from there? Like, so it's sort of a follow-up to Nina's question. So will you get the mirror dictionary for those non-abelian GLSMs?
First, what do you mean by IR in your context? There are two. What I said that I integrate some modes in the field space, but worksheet I still at IR, so I still in the geometry phase. In the UV, worksheet I still on the UV, so I still in the geometry phase. I just integrate out some modes in the field space. That's from the field space point of view. That's the type space point of view. I go from the non-abelian G quotient to a associated cardan.
So you will integrate those W bosons?
I integrate when we okay. Let me go to.
Yeah.
So when we go to when we solve in the GLSM, we usually solve the classical potential energy, and then we usually solve D term and F term, right?
Oh, I understand how GLSMs works.
Yeah. I know. For the non-abelian, the D term is for example, if a rank K, so K by K matrix, I integrate out the off diagonal constraint first. Then I go to a effective series.
I see. So
okay.
But basically, his check is going to be the following: you go in the original description of linear sigma model, so T-star Grassmannian as a quotient, or Grassmannian as a quotient. You go on the Coulomb branch, you integrate out all the charge fields, you get some effective superpotential for sigma.
Yeah, that's the point where it is for the IR. Yeah, that point definitely is IR field because I go to the Coulomb branch. That means that the parameter R. Let me go. to RG flow. So this one stands for RG flow, right? When mu is worldsheet scale. So when worldsheet is UV, so this R is go to very positive. It means your perturbative series always well defined. So when mu go to IR, so this R becomes negative. So sigma field is the expectation value sigma field is heavy. Then we can integrate out all the phi field and go to Coulomb branch. I think my description not only apply to mu to be worldsheet UV, but also IR. So the mu I can define. The mirror is defined at all scales. So, but we are using a specific IR scale Coulomb branch to compare some data. That's my strategy.
Okay. So
does that make sense to you? Yeah. For example, for CPN, this is n+1. So the non-linear symbol corresponds to the UV series that integrate some massive modes in the field space with from GLSM to the non-linear symbol, so non-linear effect series. And so the Coulomb branch corresponds to mu. What is the IR? It's the effect series. That when mu goes to 0, this one becomes very negative. So R becomes negative. The sigma field is very the expectation value sigma field is heavy. It's big, so we can integrate our net field. So go to Coulomb branch. I use that to divide some check data, but of course our proposal can define what is the UV. The associated column is just that in what is the UV, I solve the constraint from the off diagonal term or the D term, because D term right like K by K matrix. The diagonal term really looks like the abelian, the maximal torus with some FR parameter in the D term. The off diagonal just like constraint. I solve that constraint first to reduce the series to associated column. This is my strategy. But this is a non-trivial RG flow. I don't know the RG flow in details. We just assume this consistent picture here. And now the Kellerman field right up because you effect series, and you don't have to be the free series because it's effect series. So the space can be open cover or original. Okay, this CN not CN times rank G. Sorry, CN and the denote is open cover. I also have additional via orbifold free vector R charge 2 Kellerman field, which I argued before that the double boson right now be promote to a Kellerman field instead of vector multiply. This is very this is a little confusing, but from the SUSY and the Gauge series, it must be the case. Okay, sorry. And also we have the adjoint field like before, but right now it's the adjoint potential or this max gauge group T. Also we have other data that I will not mention, just like before. So now I give a consistent check like before. Like I said before, mentioned before, this is because I don't know RG4. We cannot claim we have proof because we don't know Keller potential. We cannot take T divided or like Keller potential. We get a mirror Keller potential. We didn't have proof. So it's proposal. Because this proposal, we only have to check whether this proposal is right. So this proposal satisfies a number of consistent checks, so including but not limited to matching weighting index, matching quantum complexity rings, match topological correlation function. Yes, we will see a lot of examples in this talk. So maybe a quick example is that a pure gauge group. So usually mathematicians care about geometry, so it's nonlinear symbol flow geometry. But as a Gaussian symbol, we can define more general space. For example, stack the vector space just point, just have quotient G. If G have low FR parameter, you still have a natural IR dynamic. So the mirror also should be interesting. Indeed, for SU2, we can define a mirror. For this case, there's no matter field, so the rho is 0. We have two roots. So the mirror is x1, x2. The roots data for SU2 is 2 and minus 2. So we can write the superpotential as 2 sigma times this one. And the Weyl group acting on the variable is sigma, become minus sigma, x1 become x2. You can check that the superpotential is in random under this Weyl group action. Of course, you can compute a partial W partial sigma and partial W partial x equals 0, get IR dynamic. This one is agreed. Some gauge series started in 3-4 years ago, the long flow to freedom. Yes. Now, next non-trivial example we must more care about is Grassmannian G.
You said that this last result agrees with, I didn't quite parse.
Oh,
just say it again. All you need to do is repeat. I just need to understand what you said.
Okay, in the pure gauge theory, 4 years ago, a paper, the title called "Long Flow to Freedom." They argue that this is pure SU2 group in 2-dimensional linear will flow to IR to a free series. The free series is 1-dimensional free series. So if you compute the W, partial X, partial W, partial sigma here, they give the same result. Claim in that paper. Okay. So for Grassmannian G, so it's a UK gauge as a gauge for gauging of the gauging of Grassmannian G is a UK gauge group with unfundamental fields. So the mirror is predicted to be a SK orbifold or Landau Ginzburg model with meta field YIA. So I from 1 to N, A from 1 to K also have a X nu equal exponential minus Z nu from 1 to K. And the superpotential can be written like this. So the rho is the weights for the fundamental rotation, and the alpha A nu is roots or UK group. We know this, then we can write out superpotential. Now, just like usual. In physics, we this theory define the target space UV. So we have to integrate some massive modes in the field space. We integrate sigma A, we have a constraint. We give such kind of constraint. So this constraint is data function in the passing equal. Then we can use this to eliminate some variable YNA. So just like solving YNA. Then we define variable pi A exponential minus YNA. Just plugging this will give such such complicated expression. Then plugging all this in the left effect superpotential will give this. So this actually is still not the corresponding non-infinite Grassmannian because S nu still like a UV freedom degree have to integrate out. But I will keep it because if you're really counting the dimension, this matter field is bigger than the dimension of the Grassmannian K, which is K times N minus K. However, if you integrate out X nu and solve and just like I solve integrate a sigma field, that one will reduce the right dimension. Because integral of X nu in Grassmannian K is not so trivial like sigma A field, just give a data function. I will keep it there. However, later on, we know if later on for hypersurface inside Grassmannian K, the theory will RG flow to a safety. Then X mu will give a safety central charge, where I will tell the right dimension counting there. Here I just keep this. Then I just like usual, I have a Landau Ginzburg theory. I can compute the quick root side Jacobian ring relation from these equations. Then this implies all the other index exponent YIA equal pi A, which I defined before. That is the last index. And the X nu equal minus pi nu plus pi nu. So by definition of the pi A, I just plug in this expression, which obtained from the vacuum equation computation. Then plug in will give this. Then I just algebraic computation. They'll tell you that I give a quantum ring relation, a Jacobian ring relation in the mirror that is pi a to the power n equal this one. So because we want the potential energy to be finite, that your quantum field could define at that point. So it means that x mu cannot be 0. And this force pi a cannot be equal pi b when a not equal b. Also, this one have an n solution because we have k variable. We should choosing n choosing k and modular y group. So this will give this kind of number of vacuum solution. So this vacuum solution is oracular, this is or Grassmannian. So indeed, we give the right weighting index in the mirror. Oh, question?
Yeah. So right. So yet you have to work in this larger space, right? There's not working naturally in a space that has the same dimension as the Grassmannian itself is not natural for you somehow?
For example, for CP4, the field space UV have sigma field and a phi y field. Then we integrate sigma and get integrate sigma and solve y phi to reduce the 4-dimensional Landau Ginzburg theory. That one integral sigma is just give a delta function. Here, integral x mu it's a very non-trivial, give a very non-trivial measure factor. And I don't know how to treat them just like a sigma field integral give delta function to make them low energy field looks very complicated. So I want to keep them. So the dimension counting here shouldn't just counting this one as a positive dimension. You can treat this axial field, give negative dimension. Maybe they can match the mass dimension.
You know, I think while sort of a Hori and Vafa story is natural for 2-2 supersymmetry, it might have actually been instructive to do the story with full supersymmetry.
Okay,
because the theory is more rigid and you know more.
Yeah, but for theory, the target space must be hyperkähler, right?
Sure.
And
yeah.
I focus on Kähler, so
there's nothing wrong with hyperkähler. It's better. It's more rigid.
I see.
And
so
you can reduce supersymmetry to 2 if you want by turning on some mass deformations. So it's just a little bit broken.
So you want to embed in this Kähler manifold to a bigger field space and then turn on some mass parameter and take some limit to go.
So let me give you an example why it's better. If you study full supersymmetry, then for things like so you get a manifold as a Coulomb branch, say, of a 4-dimensional gauge theory in a circle. Okay.
Okay.
You can just ask what it is. It's a hyperkähler manifold, a Coulomb branch of a 4-dimensional gauge theory in a circle. Okay. So for those kinds of things, mirror symmetry should do nothing. In other words, the spaces should be self-mirror up to hyperkähler rotation. But it's a very special construction. And then if you try to say, okay, no, this is a very exotic thing. I want something like T-star Grassmannian, okay? So, which would arise as a Coulomb branch, but of a 3-dimensional gauge theory, right? Then again, it's known, what you need to do. You need to do some compactification on one side, add some potential on the other side. So again, but you're starting from a place where it's almost self-mirror, right? I mean, the fact that Coulomb branch should be self-mirror of a 4D theory on a circle, it's easy to, to argue this physically. Anyway, so you know much more. Then here with this little supersymmetry and a theory which is interacting, it's hard.
I agree. For example, Kähler potential, we don't know the Kähler potential on the arch floor. So 4,4 maybe.
Yeah, right. And there, in fact, metrics actually would 4,4 and 4,4, which is a Coulomb branch in a circle, it's even better, right?
I was thinking about that. That's basically. Okay, good. Yeah, one can also compute a quotient function for the Vafa in 1990 he defined the correlation function for the topological B model non-Ginzburg theory. So the key ingredient for the computation is that computer the determinant or the Hessian is defined as a determinant or the matrix or the second derivative or the superpotential W. For example, for Grassmannian 2-4, I already gave you the superpotential. Then I just plug in do the computation. This one tell us that this Hessian can be computed like this.
But this is guaranteed to work. This is really no check at all, right?
Yes,
you could have written any Landau Ginzburg potential that after integrating out stuff gives the same effective superpotential for sigma.
Yes.
As your theory, this would have worked. So this is not a very strong check at all.
Oh, this is not a very strong.
A much. This is not super strong.
We can also check the partition function, but I think.
Well, I mean, Vafa would have solved the theory from these kinds of things. So this is, I mean, this is guaranteed to work, right? Once you know the critical points and the Hessian and everything else is given in terms of that, so you're done. Yes,
you're right. And yeah, maybe another. I'm just writing a paper that I found. I'm recently writing a paper that from the mirror on Ginzburg, I define Picard-Fuchs equation in a mirror. Then I can compute global weightness from non-abelian mirrors. But this will coming out. Maybe in the future I will talk about that. I think that will give a strong check, a stronger check. Yeah.
I think a stronger check, yeah, it would be to reproduce from the B model, like the quantum differential equation kind of things that.
Yes, we can get that.
Ivan compute, yeah.
Yes, we can get that.
Yes, but we don't know.
That's stronger in that what Vafa tells you, what the Vafa's construction gives you, is basically genus G partition functions of the theory, but not coupled to gravity.
Oh.
I think Ivan's results combined with I think some theorems of Telemann would tell you that the theories are the same also coupled to gravity.
Yes,
but it's unfortunately not a very strong check because.
Yes, that's definitely very strong. But the getting out of coupled gravity also open question. There's no one studied that before. I will think about that. So only what I define getting is only for genus 0. Maybe a genus 1 for defining torus partition function. For high genus, we don't know. So yeah, so we only know the topological string theory and the FGRW for in the math side. They define high genus and they consider gravity on the worksheet. But for getting us more coupled gravity, I think even in gauge theory side is a very difficult problem. But this is definitely a problem. Definitely a stronger check I should think about in the future. But right now I cannot answer. Yeah, I cannot provide that answer.
But I understand that you're checking this in your forthcoming paper with the Gromov-Witten invariant. So you know how to extract the numbers from this partition function that Mina mentioned, or?
For partition function is by there are several authors. They don't have to use mirror. They in the gauge theory side they study partition function. They extract Gromov-Witten from this partition function. The paper I'm writing right now is I using mirror to get a Picard's equation, just traditional like Candelas et al. Did. I get from mirror, I get a Picard copy. In a mirror, I define Picard's equation. And Picard's equation can tell you the first period pi naught, and the second pi 1, and pi over pi naught, we define flat coordinates. And flat coordinates, and plugging all this data in the Picard copy, and doing instant expansion. The coefficient will tell you the Gromov-Witten invariance. This is what I'm doing right now. The partition function is without using mirror. So this is a completely different story.
I see, okay.
Okay, maybe correlation function is not stronger, but I still want to finish in my talk to talk about that. So I give you Hessian, then we can compute the correlation function. Then this match the classical correlation function or A model. And we can using Carrier relation to divide high power correlation function that match the A model result. So one can start a more general, more complicated foreign sample procedure as for Grassmannian. Then we can compute a correlation function in match This has been done in my paper with Eric last 3 years. Okay, when I say bit twist, I already assume my space.
Sorry, before you go on, and do you understand how your results relate to Reich? Have you tried to compare to her to their results? I'm hoping to pronounce the name correctly. Somebody can correct me.
Who's the
I
result?
think it was Lauren Williams and
Colin Rich, right? Colin Rich, right? I'm not sure.
Yeah,
I'm
that's
pronunciation. Right. Okay. Yes, their result in terms of G mod P, so they don't realize the geometry and the space as a V mod G. They write it as G mod P. So their mirror writing is in terms of the cohomology for Grassmannian in terms of the cohomology or superclass, and they have a systematic way to write out that. But for general G mod P, the superclass is very, very complicated to write out. So this is the reason they only can. I think my impression that they only write out explicit for Landau Ginzburg or Grassmannian or the mirror Grassmannian. So this is my answer on their proposal. So how to connect my proposal to their proposal is that how to extract the quantum, how to extract superclass from the remuneration I defined before to theirs. And I have a collaborate who is the postdoc in Harvard Math Department. She's doing such thing for flag variety. For Grassmannian, we know how to do that. Yes.
Okay. So for Grassmannian, you know how to connect, but for more complicated flag varieties, you're working on it. Is that the answer?
Yes.
Okay.
So yeah, I always say I can do. I'm using the B-twist of topology Landau Ginzburg theory to do the computation. So I already assume it's B-twist, but we know that only Calabi-Yau can do B-twist. So we have to check whether our space is B-twistable because we are not fundamental theory. We have orbifold theory. You have to make sure your homomorphic top form should be gauge invariant. So the homomorphic top form for the field space can be written like d sigma, yg dy, and yg dx mu. So the y simply permute them. So it's not exact Calabi-Yau, but only up to some plus minus. So, but for closed string, this sign ambiguous okay for doing B twist because if you remember the parting function in the B side is z equal topological form by yg by integral, right? The classical contribution gives the full information. Then if the homomorphic top form have a sign, but we know the
no, but this is too fast. You don't know really the homomorphic. You know the period, but you don't know which part of that is the potential and what part is the homomorphic form.
What I said that, okay, yeah, it's too fast. Okay, let me be slowly. Okay, what I said that when I do B-twist, I require the Landau Ginzburg theory is a non-compact Calabi-Yau with a function. I only require the space should be non-compact Calabi-Yau, right? My space for define Landau Ginzburg is a Weyl orbifold theory. So I have to check that space should be, the field space should be a Calabi-Yau or very close to Calabi-Yau. So the homomorphic top form or that space just simply write this factor. Then the Weyl simply, orbifold will exchange this variable. And then overall, they will have a positive minus sign. So for positive sign, it's a Calabi-Yau, everything is okay. For minus sign, this started in this paper by Eric. That's this negative sign also can. So the negative sign also can do the B twist. Does that make sense?
I still don't understand. I mean, to say whether it's Calabi-Yau or not, you need to know the space, but you don't know the space because all you know is some effective theory where you can integrate out as many dimensions as you want, and you're still okay. So you don't really know the space. I mean, you could try to guess what the space might be, but at this point, it seems to be whatever you do, it's a guess. You could try to get something of the right dimension, integrating out the right number of fields, but it's still a guess.
My point for the, okay, I got your point. You said that what's the Landau Ginzburg theory corresponding to, right? I don't require Landau Ginzburg correspond to anything. The Landau Ginzburg theory defined is a non-compact Calabi-Yau with a function on that non-compact Yau. I just want to let a non-compact space should be a Calabi-Yau. This is what, then we can do B twist. if you do W, the supertensor quasi homogeneous, it can be also do A twistor. That one, let's have a chance to be a Calabi-Yau geometry. It's a compact Calabi-Yau geometry. But I just test the B twist. I don't talk about any A twist or this. So B twist only requires.
But I still don't know that you actually know what the target is, right? Do you?
The target space is just the non-compact Calabi-Yau with.
So okay. So,
yeah, yes,
sorry.
I do.
So what you're
yes,
saying is, take your theory that where you wrote it down with the sigma fields and the mirrors of the W bosons and the mirrors of the matter fields, and say, let me declare this to be my theory.
Yes.
Okay. Let me just declare this to be my theory. So the target space is C star to some large power.
Yes.
Right? Maybe modulo Weyl group.
Yes. That's
plus
the
some
space
potential.
I'm talking.
And you're asking if you can do B modeling. Yes, you can do B modeling. That's right. Sure.
Yes.
Okay.
Yes.
No,
but I have to check that space in the top form. I mean, is should be invalid on the Weyl orbifold, right? Because orbifold, this is my motivation.
Yeah.
Okay. It's a general proposal for non-abelian. So I don't restrict to Grassmannian Kn. For example, I can start a pure gauge SO3. So we call that a mirror for SU2 gauge group. They're defined like this. So for SO3, the weight, the Lutz data are a little bit different. It's 1 minus 1, not instead of 2 minus 2 in SU2. And the SO3 have a non-trivial pi Foster homotopic group. It means that you can also turn on we call discrete theta angle. And so in this SO3, we can turn on this discrete theta angle. Then this theory, then we can compute if you define sorry, a little bit tight. So we have given such superpotential. Then we compute a critical root side. Then we find that only you turn on I pi discrete theta, non-trivial discrete theta angle, you can have a non-trivial IR vacuum. So in this sense that SU2 really can float. Maybe I can talk about that later. Sorry, I don't want to confuse you. So one can also find a more general SOK group in my paper with Eric. And one can also study some other groups follow the same procedure. That I will be quick about this. Just do a computation. We tell some IR dynamic, and also you can do a consistent check. Follow the group. For example, SU2 is called SP2. Then we start from two different Landau Ginzburg relation match. Indeed, they are match. Also, we are not restricted to after to Fano. We also can start a hypersurface in Grassmannian. This is maybe for Gmod P or maybe for some Fano space. Mathematicians have other way to write out mirror, but for hypersurface, I didn't find any paper talk about that. So hypersurface should be a non-trivial thing, a non-trivial mirror we should write out. So for now, just consider simple case. Consider Gaussian for hypersurface or degree D in Grassmannian Kn. So the Gaussian will describe this is UK gauge group with unmet field, and also have a P field. It's a charge minus D under the determinant potential of UK, such that we have a gauge minus superpotential W equal PG, and the G is in terms of Bayesian field defined like this. Maybe in math they call Poker coordinates. Yes, maybe yeah, if I remember correctly. So yeah, because we want to go to geometry phase, then phi should be taking non-trivial expectation value. The R symmetry shouldn't be break. So it means that the R child of phi must be 0. We know W have R child 2, so it means P have R child 2. So it means that P have takes expectation value must be 0. Then the mirror, because we know the data, we just write a mirror. We know the roots, we know the weights or representation. We just plug in the framework or the mirror proposal. Then we have such formulation. I will give some comment. Let me give some comment here. For yi, the variable is still yi. The fundamental variable is still yi. Even the physical variable is exponential yi. The fundamental variable is yi in the past nickel. It's mirror to phi ia. So xp, the fundamental variable for the corresponding p field is not yp, rather it's xp. The reason is that I start with a theory that have non-trivial R child 2. So if you define your T duality on the watershed which is fair, this R child 2 on the T-duality have a non-trivial factor in the mirror. This thing is missing in the original Hori and Vafa. So in my paper, we take into this account, suggests that the mirror for the non-trivial R charge we are changing from variable from YP to XP. For more general R charge,
can you explain again? How does the fact that explain again the story of R symmetry, and how does it tell you that the right variable is X and not?
Okay. Yeah. So. Okay. So. So if you have a non-trivial R charge in the A side, in the gauge theory side, then you can turn, if you then maybe you can gauge that you turn on some AR field for that non-trivial gauge R charge. Then, for example, if you do A twist, you should gauge some.
So, for example, if you have a non-trivial superpotential, then you have to.
If you have a non-trivial superpotential, for example, let me go to last slide. For here, W equal PG.
Right.
In the geometry phase, the phi have R charge 0 and P have R charge 2. Then, if you define what sheet is not a flat version, rather is sphere, because if you R follow to safety, right? Safety, the flat physics is same as sphere physics. So for sphere physics, if you do the T duality, the R charge will give a non-trivial factor in the mirror on the T duality for the same procedure you're usually doing T duality. That factor.
Sorry, on a flat world sheet, how does the R charge enter T duality?
If you see the follow safety, then the flat physics, if you do special component transformation, the flat physics is the same as the sphere physics, right? And then if you want to see define on the sphere, the R charge and take the T duality on the sphere physics, the R charge on the T duality will not disappear. They will give a non-trivial factor in the mirror. This mirror tell what the mirror variable should be.
Sure. I mean, you should indeed be able to compactify both theories on curved Riemann surfaces, and then you will be sensitive to such things.
Yes, yes. But the flat version will not find that.
Okay, so where concretely does it show up for you? What does this fact tell you?
This fact, what the fact tell me that if you have non-trivial R charge, the mirror variable should not be Y, rather instead of X. For example, R charge 2 is XP. This net R charge tells me about that. On the T duality. How? Okay.
I mean, what's the right variable versus whether X, P, or Y sub P is a question about the metric, right? When you study the metric, is the metric dx over dx over x, or the metric is just dx, right? That's the difference.
Yes. Yes, right. So if you have the matrix also have a if you change the variable, the matrix also change. This is also discussed in our paper. But because the matrix is an irrelevant term I mentioned before, I will not talk about that specifically. So you're right.
Okay.
Maybe if my answer is not satisfied, I go some detail here. Okay, the X mu also have such exponential of Z mu is just because this one also have R charge 2. There's a reason why I have a log X mu here. So this log term.
You just want to say that you should be able to couple it to a gauge symmetry, and then you don't want it to act just by shift.
Shift.
Okay.
Sorry, could you repeat?
Okay.
Yes, I usually T duality apply to a gauge theory, gauge field, right? A mu. I also gauge the asymmetry in the A twist, right?
I mean, the mirror theory could have logarithmic charge. It's not strange.
Yeah, it's not strange. If you take it as an effect theory, it's not strange at all. But if you're searching for fundamental theory, it's strange. But if you take it as effect theory, the field space will dynamically exclude the point that X equals 0. because there are some net place were missing some freedom degree. However, that missing freedom degree will not affect your IR series, so we're not giving new Weyl index, or we're not changing correlation function, we're not changing partition function, or changing other things. I think it's fine.
Okay.
Okay, now I just like usual, I integrate a sigma field, then solving this constraint. And let me be quick about this. I just finally will get a effect supertension from integrate of some sigma field and solving some Y field, and have such formulation. Yes, this is supertension. So I will not compute other quantity, but I want to compute a dimension, because the X mu have a really tricky dimension, X mu. Because in mathematician, they claim the mirror, the dimension must be matched, right? So for the final case, the X mu really looks like positive dimension, looks confused. So here, if you follow safety, there's no confusion, because safety have a very robust counting of the dimension, because the central charge over C can be treated as the IR dimension of your touch space. And for the Landau Ginzburg, which is quite a homogeneous polynomial, the dimension can be counted by sum all this 1 minus Qi. Qi is R charge of the matter field in the supertension. So the P, because the W here have a R charge too. So all the linear polynomial must be R charge too. So this one have R charge too. So this one have R charge too. So all this have R charge. I give 0 if we take exponential. Then I just plug in this R charge and with the number do the computation. Indeed, they will give the same dimension for the hypersurface inside Grassmannian G. So this suggests that the dimension really also match. Although in final case, X mu looks like a positive dimension, but no, it's not. Also, it suggests that we could have a mirror geometry, right? I just talked about Landau Ginzburg. Maybe we can change the Kähler parameter to a geometry space. Yeah, this should left to future work. Okay, I already talked about some examples. There are some duality in the gate series. They call it's very close. It's very similar to the 4D Seiberg duality. It's found in 2011 by Hori. I call it 2D Hori-Seiberg duality. So Seiberg duality is two different gates, two different geometric coefficients. They follow same non-energy theory. In his paper, he focused on clarity, also it's same CFT. So maybe they have a big story in there. I will just use simple example to start with. For example, I consider O2. So it's a non-kinetic gauge group. So the gauge theory has Z2 orbifold, and the vacuum can intersect this orbifold. Unlike the Weyl orbifold, that our vacuum never intersect that, will never consider twist sector. Here, the Z2 orbifold can intersect, the vacuum can intersect this Z2 orbifold. It means that in some cases, I have to take into account twist sector to give the right number of vacuum and the right number of correlation function. I will tell later on. There are two different, orbifold theory, O plus or minus, defined in the Hori's paper. Roughly speaking, the O plus keep the twist sector, or minus project out. It depends on the number of matter fields and depends on other data. So now I consider a very simple case, O plus 2 gives you with 3 doublets. So the mirror Landau Ginzburg orbifold has 6 field YAI as well as 1 sigma. So O2 really close to U1. If you change it's really close to U1. So that's just 1 sigma. And then the supertension just plug in the data. We also turn twist mass, because if you have in your gate theory, if you have some failure symmetry, you can have freedom degree to break this freedom symmetry by turning twist mass. So in a mirror, it have such kind of mirror twist mass turn like this. As this has already been defined in Hori and Vafa original paper. I will not tell more detail about this. I just tell this is well defined. The Z2 orbifold acting on sigma become minus sigma, and Y1I, Y2I, which change them. So you can check that the supertension is in band under this Z2 orbifold. So the supertension is getting band. It's a physical supertension. Now one can again do the computation by studying vacuum equations. Roughly speaking, is this So this vacuum will not break the Z2 symmetry because the Z2 acting on the X become minus X. So the vacuum equation of Weyl. So this one has 3 solutions. One is 0. The other one is X naught minus X naught, some function in terms of twist mass mi tilde. And for the X plus X naught and minus X naught, because the Z2 orbifold is orbifold, it's a gauge theory. So the connect them, so should be treated one single solution. However, for X equals 0, the solution intersects with Z2 fixed point. So we have take into account twist sector. For this case, the twist sector is just 1. So X equals 0 have 2 vacuum solutions plus only 1 to give 3 vacuum solutions. One can also study another gauge theory called SO gauge theory with 3 doublets and 3 singlets and a superpotential, and write a mirror and do the same computation like I did before. We'll give the same number of vacuum solutions 3 here, but the expression different. X equal not here for the SO2 group, just give 1 solution because we have no Z2 orbifold. And the X plus and X minus now should be treated as 2 different solutions because right now Z2 is a global symmetry instead of Z2 orbifold in the O2 case. And 3 equals 3. It's agree with that. They should claim that this should be a subduality. One can start a more general case in this paper with Hardy and Eric last year. Okay, maybe a brief summary or other relevant development in the non-abelian mirrors. So in this paper with Eric and Hao, so we studied a 2D non-abelian pure gauge in the mirrors. I give a refined dynamic. What I mean by refined, in the paper by I think Seiberg or Vinich and Ahom, and I forget the other author name. Forget the long flow of Freud. They argue that for SU K gauge theory in the gauge theory side, they flow to a K minus 1 free K minus 1 number of free series in the IR. In the mirror, we can give a more refined that, for example, for SU2, they can decompose SO3 without a discrete theta angle plus SO3 with this non-trivial discrete theta angle, which is the example I mentioned before. Only SO3 with discrete theta angle give a non-trivial IR vacuum. So SO3 with no discrete theta angle will break through C. So this argument also be checked by computer Elliptic in the gauge theory side by Eric and his collaborate. Okay, the second paper we computed a massive orbifold Landau Ginzburg model correlation function and check a 2D Hori-Seiberg duality. So in Vafa 1919 paper, he didn't include the case that if the orbifold is a massive orbifold. For massive orbifold, the trace cell will not contribute because if you have to do non-trivial, if you want to get a non-trivial contribution from trace sector, you have to go to high genus to get high genus. For high genus, for massive theory, net one contribution must be 0 due to some selection rule. However, for massive theory, massive orbifold, for example, Z2 orbifold, the twist sector will give a non-trivial Hessian. So we have to take it into account. So in this paper, I take into account that to compute massive orbifold Landau Ginzburg theory. So the last one is we also extend for 2D 0 gamma to non-abelian mirrors for funnels. Okay, conclusion that I just reviewed Hori-Vafa construction or mirror to abelian Gaussian symbol. I give a proposal for mirror to non-abelian Gaussian symbols. I discuss several examples and showing matching correlation function and the rings and the weighting index. And thank you.
Thank you.
Any further questions?
Yeah. So what I was trying to say is that say if you take a Coulomb branch of a gauge theory in type A, right? Then a Coulomb branch of a gauge theory in type A, say three-dimensional gauge theory in type A, right? Is again turns out to be a quiver variety of type A. In other words, it again has a description as a nonlinear sigma model. Sorry, as a linear sigma model with a non-abelian gauge group.
Okay.
But it's hyperchaotic.
Yes.
Those theories you can mass deform, turn on some equivariant parameters, and for those, the mirrors are known. Okay.
I see.
Now, that works if it works in some larger generality, but connection to gauge theories in 3 and 4 dimensions is crucial.
Yeah, you're right. Yeah.
What would be nice to do is to generalize this for more general things that don't necessarily come from, you know, Coulomb branches or anything, right? Which you can easily write down. So.
Yeah, you're right. Yeah, I will think about it.
Okay. I should say the reason it's nice is the following: that understanding topological mirror symmetry is a fine thing to do, but really, the string theory tells you that there's a much nicer, bigger package if you really get things right, which is not just for topological string amplitudes, but also for branes. And in other words, you also get homological mirror symmetry and SYC mirror symmetry. So really, you want to understand those 3 things together. And if you try to understand how mirror symmetry works in presence of branes, then it's a much finer, like it probes your theory much better, right?
You're right. Today I just focus on closed string, but I do study brain, just something I'm writing. And I say I check topology. Doesn't mean that our proposal is just for topology. For example, for the Hori-Seiberg duality, they not only have AC ring but also have CC ring. So in the mirror, we also check where's the AC ring, where's the CC ring, where's that. So I think it's a physical mirror. But today I just focus on a small piece of that, something that way can be easy to present. Other maybe require some twist set computation or something very complicated technique.
Other questions?
I also have a question to you. You have a paper with Hori and David Tong. I forget last author, maybe near 4 author. You connect 3D mirror symmetry to 2D.
Yes, that's right.
My question is, for 3D unequal 2, the Coulomb branch and Higgs branch is unambiguously defined? I mean, did you get my question?
I didn't.
How to say? So for 3D, you're using idea that 3D unequal 2, that the Coulomb branch, the Higgs branch exchange name, then reduce the 3D to 2D, get a mirror Hori-Vafa conjunction. My question for 3D unequal 2, whether the Coulomb branch and the Higgs branch is unambiguously defined. In some situations,
the theories we studied there were abelian gauge theories. So there, everything can be made very explicit, and it just, you know,
I see.
But again, the better thing to study is to study mass deformed n equals to 4 mirror symmetry, because it has more supersymmetry. And once you understand that, you can still recover. You know, you can turn on some larger deformation yet, where the theory is pure n equals to 2. But it's, you know, thinking of this as coming from a theory with more supersymmetry is better, because you know many more things.
Yes, you're right.
Yeah, just maybe to add on this. So that mass parameter that you're mentioning, you can increase it, you can send it to infinity, and that would actually lend you to like actual, you know, genuine n equals 2 theory. But sort of it's embedded into this larger framework.
Yeah.
N equals 4 theory.
Yes, I agree. Because recently we studied, I also have paper, just have paper about 3D quantum key theory. And for Grassmannian and KN, so the roots have a non-trivial transformer level. We get the letter level by embedding it to n equal 4, and then with more matter field, and then turn twist mass go to infinity, some mass go to infinity. So we tell you what's the transformer level on that, all that. So I think on 3D really n equal 4 really tell a lot of information. I appreciate what you guys say.
Yeah.
That's right.
But yeah, and right. So you're at Harvard, right? So I encourage you to talk to mathematicians, because in the time of Hori-Vafa paper, they've learned a lot. They've studied mirror symmetry, and they've learned, for example, that, okay, Aru is there, right? So he will explain at Harvard, right? He'll explain how the mirrors that Hori and Vafa wrote down are actually not entirely completely correct. I mean, they're correct, but there's more to the story than just what they wrote down. And that actually has nice connections to physics as well, and
I see.
the wall crossings and so forth. So
yeah. He using counting homomorphic disk, right?
Yeah.
I know him. I personally in this direction just coincidence. I didn't know any math thing. I just found this question interesting and I saw it. So I don't know many math history, but I definitely will take your suggestion. I will talk to them.
And yeah.
Yeah,
and the story is very nice because his wall crossing is related to wall crossing of Gayota, Moore, and Aitsky, and it's a very beautiful story. So one should pay attention to it. And
okay. Yeah.
And it will certainly hit you as well. There's no way that this is not going to be even more interesting for your story. So.
Right. You're right. Yes.
Okay.
Thank you.
Even this wall crossing in the J function computation, or which?
No.
No. Wall crossing where? In this J function computation?
No, when he's trying to write down the superpotential. So the superpotential makes sense. However, the space you're writing it on doesn't. In that, the superpotential is obviously it's a holomorphic function, but it describes your mirror only in one small patch, and then you have to understand how to extend the coordinates elsewhere.
I see. Mm-hmm.
Yeah.
Great.
Okay.
Okay.
All right. Thank you.
Thank you very much.
Thank you, Wei. Thanks, bye.
Thank you, Pete. See you.
Bye, everyone.
Bye, everyone. See you.
Bye.
Bye, Miroslav.